Hello, geometers. This is Miss Backfish, and I am here to help you review for your similarity unit test. So this is a review I gave to my students, in case you're not one of my students, to help them review, and I'm just going to work through it. And if you're not one of my students, hopefully you have been looking at some similar material, and some of this may help you, but keep in mind, this is not intended to be everything your teacher might have gone over with you. In case you're not one of my students, you might have done some different types of problems that you need to go back and look at quizzes or homework to see. So for this first problem, it says in triangle ABC, and it gives me some measurements of angles. Measure of angle A is 57, measure of angle B is 48. Then it gives me information about another triangle. What I'm going to do first is I'm just going to draw two triangles, and I'm not trying to draw them in a particular way. Like I'm not trying to make the angles look like they're 57 or 48. I'm just being very generic so that I can have a mental image of comparing these two triangles. So A is 57 degrees, B is 48 degrees, and then over here it says that angle R is 48 degrees, and angle S is 75 degrees. Are the two triangles, ABC and QRS, similar? If so, by which postulate? Well, there are three similarity postulates. There's SAS, SSS, and AA. If you want to know if two triangles are similar, knowing this information or this information or this information is the only way you can know it unless you knew everything about it. But if you know everything about the triangles, then you do have these as well. So you have to have at least this amount of information or this amount of information or this amount. This is knowing that two pairs of sides are proportional and the pair of angles in between them is congruent. This is knowing all three pairs of sides are proportional, and this is knowing two pairs of angles are congruent. Okay, so remember, angles have to be congruent and sides have to be proportional, not congruent, but proportional. So here, I don't know anything about any sides at all. So when I look at this and I say, well, there's nothing about any side lengths, I can't possibly compare to see if the sides are proportional. So I'm going to be going for this. I'm going to be wondering if maybe I can prove AA. Well, I have two angles in each triangle, and no, those two angles don't look congruent, but there's a missing angle in each triangle. So what if I find one of the missing angles, and it really doesn't matter which one? How about this one over here? I know that all three angles add up to 180. So 180 minus 48 minus 75 tells me my missing angle would be 57. And then, yep, I have one pair of angles congruent and another pair of angles congruent. That's two pairs of angles congruent. So by angle-angle similarity postulate, those two triangles are similar. Keep in mind the reason it's just angle-angle is because if you have two pairs of congruent angles, then you automatically have three. Because if I subtract these numbers from 180 and also subtract these numbers from 180, it's the same numbers. So I'm going to get 75 either way. So if two pairs of angles are congruent, then it's automatically all the angles are congruent. Sometimes, keep in mind sometimes that these questions will ask you then to write a similarity statement. And in this case, it would be something like this. Oops, excuse me, triangle QRS. And the order of those does matter, but this one didn't ask me for that. So let's go ahead and look at the next one. It says in triangle MNP, again, I've got two triangles, so let's just go ahead and draw two generic triangles. I usually draw two kind of almost equilateral looking ones. MNP and JKL. In MNP, M is 67 degrees and P is 52 degrees. In JKL, K is 58 degrees, and then there's a typo here. It says S. That should say L. Angle L is 52 degrees. Are the two triangles MNP and JKL similar? Well, we need to find a missing angle, either place. Let's find one over here this time. Let's subtract 180 minus 67 and 52. So 180 minus 67 minus 52 gives me 61 degrees. Well, I could go ahead and find this one if I want to, but I already know I don't have two pairs of congruent angles. I have one pair, but then neither one of these is 58, so there's no way to have two pairs. Because if you have two pairs of congruent angles, You have 3 pairs of congruent angles. So, even if theoretically, well, it can't be, this one can't be 61 or 67 because the other one would be 61 or 67. So in other words, even though theoretically we don't know what this angle is, it can't be a matching one of either one of these because then the leftover would be the other one of those. So these are not similar. So keep that in mind when we talk about the similarity postulates or theorems, but usually we just say similarity. These are my postulates, excuse me. These are my 3 similarity postulates. If it's not one of those, then it's either not similar or not possible to determine. Okay. Next comes a question several of my students were asking me about. So let's look at this. We have this big triangle and we have some parallel lines in here. How do I know those are parallel? Well, because they're 90 degrees here, 90 degrees here, 90 degrees here. Those are corresponding angles. If corresponding angles are congruent, the lines are parallel. If corresponding angles are congruent, lines are parallel. And we know that when you have parallel lines, it divides things into congruent little pieces of segments. So these 3 pieces right here would be proportional to 5. But the other thing to know is that the triangles, we have 3 triangles represented here. There's the big one, YPN, and then there's the medium-sized one, YKC, and then there's the smallest one, YMQ. Those 3 are all similar. And how do I know? Well, they've all got a right angle, and they also all have angle Y. That's 2 pairs of angles. So they're all similar by angle. So all 3 triangles there are going to be similar. Now, what you got to be careful about is to recognize, for instance, that YC does not have a length of 5. It has a length of 5 plus 5. So over here, YQ is just 5. YC is 5 plus 5, which is 10. And YN is 5 plus 5 plus 5, which is 15. And then PN is 12. So if I want to find KC or MQ, I'm going to compare 5 to 15 and the missing side to 12, or 10 to 15 and the missing side to 12. So I've got YQ, oh, there's my cat. Excuse him as he goes on his merry way. 5 over 15, I think he's about to come back, equals MQ over 12. And then up, there he is. Wave bye-bye. He's polydactyl. Do you see how he has extra toes? It's a special thing. All right, cross multiplying here, we get 15 times MQ equals 5 times 12. And then divide both sides by 15. And I get MQ is 4. There it is. We'll do the same thing to find the missing side KC. We can say 10 over 15 equals KC over 12. Ten times 12 is 120. 15 times KC equals that. Divide both sides by 15. And KC is 8. And we already answered the question, how do you know the triangles are similar? We already said by angle. So we've got all the information we were asked for at this point. Moving on. Okay, so for this page, we have some parallel lines. See all those arrows? All those arrows are pointing out parallel segments, really. And I want to remind you that if you have parallel lines, either with a triangle or it could just be lines crossing through other lines, okay, that parallel lines divide these segments into proportional parts. Okay, so for instance, if this is A, B, C, let's go with J, K, L, that I could say A over B equals J over K, or I could say C over B equals L over K. Things are proportional. Everything's proportional. I could say A over J equals B over K. As long as I'm consistent in the way that I'm going here in terms of my comparison, K over B equals L over C, then those are all proportional. But what that also means, let's say if B over C is proportional to J over K, if those two ratios are equal, then another thing that tells me is that if I wanted to add them up, I could. I could say B over B plus C, this part over this whole part, equals to K over K plus L. K over K plus L. So pretty much what I'm telling you here is that when you have parallel lines, it divides things up into proportional pieces, and that includes big pieces and small pieces, as long as you're comparing things that are alike, like compare two big pieces to each other and two small pieces to each other. All right, so for instance, what that tells me here in number 1, the question mark and the 6 I can compare to each other, and then I can compare the 30, which is this whole side, both pieces, to the 18, which is this whole side, both pieces. I don't have to subtract and find this part right here because it would be hard for me to know what to put for this. I could do it, but it'd be easier if I just go ahead and compare the whole side, both pieces put together, to this whole side, both pieces put together. So in other words, let's call that X. X over 6 equals 30 over 18. That's not the only way you could set it up. You could also say X over 30 equals 6 over 18. If I set it up one way and you set it up a different way, the way for us to know if we're both right, because there are like 8 different ways I could set up a correct proportion here, is if when we go to cross multiply, we would be cross multiplying the same thing. If the cross products will give me products of the same two things, like in other words, 18 times X and 6 times 30. All right. If your cross product was 30 times X, then that's not the same as my proportion, and it's not true. Okay, but as long as you're multiplying the 30 times the 6 in one way or another, and the 18 times the X, then we've really written the same thing. So 18X equals 6 times 30. So 18X equals 180, and X equals 10. Next, over here, we have 16 and 20. And again, we don't know either one of these pieces. So it would be kind of hard for me to figure out both pieces. I would have to say this is X and that this is 81 minus X. So it'd be a little bit more algebraic than I have to be. Instead, I can just say, let's call this X, and that goes with 20, and then compare the 81. So to compare the 81, I have to compare it to this whole side, both pieces put together, which is 36. So I can say 81 whole side over little piece of the side here equals whole side over here over a little piece of a side that goes with X, 20. We wouldn't want to compare the X to 16 because X 16, let me get a different color here, 16 is comparable to this part here. The 20 and the X go together. So 36 times X equals 20 times 81, which I believe is that. And I divide both sides by 36, and I get 45. So X is 45. Same thing down here. On this one, you do have to be careful because they're kind of trying to trick you. Like we were saying up here, don't compare things that aren't alike. this part here goes with this part here. This part goes with this part. So I'm not going to compare the 3. I think it will be to my benefit to subtract 3 from 5 and get a 2 for that, because that's the part I need to compare to the question mark or the X. We'll call it an X. So then it's 10 over X equals 10 is the whole side, so I'm going with 5 over 2. Cross multiplying gives me 5 times X equals 10 times 2, and X equals 4. And finally, this one is more the way we're used to looking at it. Instead of adding up and talking about a whole side versus a piece of a side, they're all pieces. So I would just say piece over here equals piece over piece on the other side. 16 over X, I'm using X instead of a question mark, equals 12 over 9. And then I have 12 times X equals 16 times 9 is 144. And that goes very nicely because 144 is 12 times 12. So there we go. Okay, so next up here, I am looking at some triangles and determining whether or not they're similar. Remember, there are 3 different ways we can find out that they are: AA, SAS, SSS. So looking here, the first thing I'm thinking is, I don't see any angles. I don't see a right angle symbol. I don't see anything with degrees. There's nothing about angles here. There's not even things like vertical angles that I can fill in myself. Okay, so it's very unlikely to be AA, and it's pretty unlikely to be SAS. It's probably going to be SSS or just not similar. So let's compare. Key thing when you're comparing is make sure you compare the sides that should go together, meaning I would start with the smallest. The smallest side on this triangle here is 15. So 15 over, then I look at the smallest side on this triangle, and that's 25. And I'm checking to see if it's equal to, the next biggest one here is 30. Next biggest one here is 50. And then finally the largest one and the largest one. Now, ways I wrote equals. We don't really know that they're equal yet. I'm trying to check that out. Though there are several different ways I can check that out. The way I'm going to do it right now is just turn all of those into decimals. Turn all of those fractions to decimals. So I've got 15 divided by 25. A fraction means division. 30 divided by 50. And 33 divided by 56. I know you guys know that, but it's just something we tend to forget. Uh-oh. This is not equal to the other 2. So it's not SSS. It's not anything. They're not similar. All 3 pairs of sides are not proportional. Over here, same scenario. I don't see any angles. I don't see anything I'm supposed to know about angles. Nothing that I'm, can figure out about the angles. So I'm looking for either SSS or not similar here. So let's look for smallest side here. And, if you wanted to, you could do, let me just hold my thought. Smallest side here is 25. Put it over the smallest side here is 15. I just happen to be putting the larger one on top. It really doesn't matter as long as you're consistent. Like if you're going to do larger over smaller for the first fraction, you got to keep doing it in that order. So then 35 over 21 and 40 over 24. So I'm going to check and see if all of those ratios are the same. In other words, all of them are proportional side lengths. And I'm just doing that by changing them to decimals. And look, we're getting exactly the same thing for all of them, 1.6 repeating. Helpful hint is when your calculator says that, it doesn't really have a 7 at the end. The calculator is just rounding just like you would when it gets tired of writing, when you get tired of writing decimals or you're not supposed to keep going. The calculator can't keep going forever, so it rounds. So it's really 1.6 repeating forever. And yeah, they're all the same. What's 1.6 repeating forever? It's 5/3. And that's what my similarity ratio here would be from the top one to the bottom one. It's what every single one of these simplifies to. That's the other way you can check these. Come on, click. is to change them all to fractions. And then your calculator will simplify for you, or you could simplify them. I said change them all to fractions. They're already fractions. But to simplify them, simplify your fractions and see if you get the same thing. If you're checking that way, if you're checking to see if, by simplifying fractions, you should have literally exactly the same fraction every time. And we do. It's 5/3. Looking down here, these are arrows. Remember that arrows tell us things are parallel, and that's a way of giving us information about the angles. Seeing that things are parallel, that segments or sides or lines are parallel, tells us, well, it tells us all 4 things that we learned in an earlier unit. Alternate exterior angles are congruent, corresponding angles are congruent, consecutive interior angles are supplementary, blah, blah, blah. The main 2 you're looking for in a scenario like this, the ones we use most often, are either alternate interior angles or corresponding. In this case, it's alternate interior. And remember, alternate interiors do kind of a Z shape. It can be a backwards Z or a sideways Z, but it's Z-like. Those are alternate interior angles. And I have another pair going the other way. Right there. Okay, that's 2 pairs of angles right there. I actually have another pair of angles I can tell you is congruent because I have vertical angles right here and here. So these are definitely similar because all the angles are congruent by AA. And finally, look, we've got 1 pair of angles and 2 pairs of sides. So which do you think we're going for here? Probably this. If they're similar, it's going to be by side angle side that we know it. Notice that the angle that we're looking at is the angle between the 2 sides we're going to compare, and it has to be for side angle side. If it's not the correct angle, if it's not the included angle between the sides, then you can't say side angle side. So I'm going to compare the 14 and the 15 to 63 and 62. And it's important that I pay attention to the order here as well, because I have to compare the smaller side on this triangle, 14 is smaller than 15, to the smaller side on this triangle. So 14 over 62, and I'm checking to see if that's equal to 15 over 63. I don't really know that it's equal yet. I just wrote it that way. So 14 divided by 62, 15 divided by 63. Those are not exactly the same, so nope, not similar. This is a good one to show you another way of checking to see if a proportion is a true proportion, if the ratios are equal, is cross multiplying. 14 times 63, and then the other cross product would be 15 times 62. If those were equal, I would get the exact same number both times. So nope, not similar. Okay, next up, this one is telling me that they are similar. It's saying that they're similar, but it's also telling me what goes with what, so that's important. So, for instance, LU, first letter, second letter, goes with LM, first letter, second letter. So that's over here. So always make sure that you use a similarity statement, if you're given one, to realize what goes together, what's supposed to be corresponding. So 6 over 54 is supposed to be equal to TU, that would go with MN. Yep. So this over this. And I'm just using random markings just to kind of point out which ones go together. So TU over MN. Be careful that when you set up your proportion, if you start with this triangle for this side, this triangle goes on top, then this triangle needs to go on top for this side as well. Okay? So 6 times, well, when I'm trying to decide what I want to say first here, sorry. When I cross multiply, remember that you're multiplying an entire denominator by the entire numerator across from it. So if you have a plus or a minus in that numerator or denominator, you have to make sure you multiply the 54 here by that entire thing. And the way we do that is by putting it in parentheses. 54 is multiplied times all of 2x minus 4, not just times 2x, but times the whole thing. And 6 is multiplied times all of 36. Okay, so this means I'm going to do distributive property. So 54 times 2x is going to be 108x. I like this blue better, don't you? I should have been using it the whole time. And 54 times 4 is 216. And over here we have 6 times 36, and that's 216. Now I need to get x alone, so I'm going to add 216 to get rid of the minus 216. And that gives me 108x equals 432. Divide both sides by 108 to get x alone. And it goes 4 times, so x is 4. You can use your calculator to check that. And that's all I'm being asked to do here, is to find the missing value. Okay? How do I know that's what I'm being asked to do? Because I believe it said it at the very bottom of the previous page, solve for x. Anytime you solve for x, you do want to go back and look at the problem and say, hey, did they ask me for x, or did they say find tu or something like that, where I would have to go back and plug x in. All right, next I'm told that KLM is similar to KRO, so KL goes with KR, okay? So 24 over 12 equals KM is first letter, last letter. That goes with KQ because that's also first letter, last letter. So negative 4 plus 2x all over 6. Again, when you have a plus or a minus in your numerator or denominator, you have to make sure you use parentheses. Set it up for distributive property. And that's what I just did. Equals 24 times 6. All right. So distribute now. Negative 48 plus 12 times 2 is 24x equals 24 times 6 is 144. I'm getting x alone now, so move everything else away from it. That gives me 144 plus 48 is 192. And then I'll get to divide both sides by 24. And that gives me 8, I believe. I'm going to check. And it sure does. So there's the arithmetic I did on that one. And x is 8. And that's all I'm being asked for. They didn't ask me to go back and plug in. If it had said like, find KM. Remember that a segment name with nothing over the top means the length of segment KM. So I would have to go back up here and say, well, let's plug in negative 4 plus 2 times x. X is 8. So that's what I'm going to put here. And then negative 4 plus 16 is 12. So KM is 12. That's if they had asked me to do that, what I would do. Last one like this, triangle LMN is similar to triangle LUT. So LM, this looks familiar. Is that the exact same problem? Guess what? It's the exact same problem. So we're not going to worry about doing that again. That's the same as number 11 directly above it. All right, number 14. A triangle with side lengths of 12, 20, and 32 inches is similar to another triangle. The longest side of the other triangle has length 8 inches. What is the perimeter in inches of the smaller triangle? Okay. First time you read that, it might be a huh? I would probably draw it. Okay. A triangle with side lengths of 12, 20, and 32. Okay. Is similar to another triangle. Doesn't look exactly the same. The longest side of the other triangle has length 8 inches. Okay. I put the longest side of this one like that. I just labeled it there. So I'm going to label this one here so that it does kind of look alike, even though it doesn't have to. What is the perimeter? Now, the key thing that we have to remember here is that your ratio of side lengths, sometimes called the similarity ratio or often called the similarity ratio, is equal to the ratio of the perimeters. Perimeter is just a length. It's like a bunch of lengths put together. So it has the same relationship as each one of those individual lengths. Meaning, if the longest side here is 8 and the longest side here is 32. Okay, so that's a 32 over 8 reduces to 4 over 1. This is a 4 to 1 ratio, basically. larger triangle to smaller triangle. How do I know this is a smaller triangle? Well, because 8 is the longest side, and even the shortest side here is 12. So that's how I know that's the smaller triangle. So we have a 4:1 ratio of any length over here to any length over here. But we just said the same ratio works for the perimeter too. So if I can find the perimeter of this triangle, it will be in a 4:1 ratio to the perimeter of this triangle. In other words, let me write it as a proportion. 4/1 equals perimeter of the big triangle, let's say big triangle, over perimeter of the small triangle. Just like it does any, like middle side of this over middle side of that, shortest side of this over shortest side of that, longest side of this over longest side of that. The perimeter works the same way as the lengths. So if I could find the perimeter of the big one, then I could call this X and solve. So let's find the perimeter of the big one. What is the perimeter of the big one? What does perimeter mean? It means add up all the sides. 32 plus 2 on E plus 12. The perimeter of the larger triangle is 64. Okay, so this now becomes 4/1 equals 64 over, and this is the one I don't know. What is the perimeter in inches of the smaller triangle? Well, in inches made me stop and think, oh no, were they talking feet or something here? No, everything here's in inches, so we're good. We just stick with what we've got. And now I cross multiply to solve. 4 times x equals 64 times 1, and 64 divided by 4, my answer is 16 inches. The perimeter of the smaller triangle will be 16 inches. You don't have to get that by individually finding each one of these lengths. You can use the fact that the ratio of the side lengths and the ratio of the perimeter are the exact same thing. Alrighty, our last page here reminds us some stuff about dilations. Now this is just asking me to talk about the rules for the dilations, but let me remind you of a few things using these pictures. Let me use this one because it's a good one. Okay, things to remember about dilations, just in general, are, as I try to grab a pencil, one thing is anytime a side length, a segment, a straight edge moves according to a dilation, the new one and the old one are parallel to each other. It moves in a way that it stays kind of angled the same way. It's parallel to where it was before. Always. That's always true about dilations. Another thing is, if you are at all unsure where the center of dilation is, points always move. Like if F goes to F prime, then F is only going to move along a line that goes through the center of dilation. So if I connect a line between F and F prime, that line automatically goes through the center of dilation. So that line goes through the center of dilation, and finding a different color over here, the line between G and G prime has to go through the center of dilation, and the line between E and E prime has to go through the center of dilation. So where do all those lines meet? At 0, 0, and that must be the center of dilation. They already told, well, they kind of told me that because all the answers here are origin, about the origin. That means the center of dilation is at 0, 0. Okay, but if you didn't know, if you were trying to find the center, that's how you would do it. You connect any point and its image and draw a big line that keeps going past them, and you do it again with another pair of points, pre-image and image, and again with another pair of points that are pre-image and image, and where all those lines meet, that's your center of dilation. All right, so another thing I need to remember about dilations. If K is my scale factor, then a scale factor of anything bigger than 1 is an enlargement. And a scale factor smaller than 1, but we don't have negative ones, so we just say between 0 and 1, is a reduction. It gets smaller. So that can help us decide what scale factor this is, because that's what all those numbers are supposed to be, is a scale factor. So first off, and it's hard to see on this one, but I have to figure out where the ones with the prime are. It's JKL. One triangle is JKL, and the other triangle is J prime, K prime, L prime. Whenever it's like that, the primes or the apostrophes, those are always the image. We go from this to this. This is the result, the image. This is the pre-image. So going from here to here, if J prime, K prime, L prime is larger, that's an enlargement. If J prime, K prime, L prime is smaller, that's a reduction. It looks like K prime is out farther than K. In each one of these, the one with the prime looks farther away from the origin, so it's an enlargement. It got bigger. It went farther away from the origin, which means my scale factor has to be greater than 1. So that rules out A. The next thing I have to do is figure out how can I tell whether it's 2 or 1.5 or 2.5. I would look at distance to the origin if that's a possibility. In this one, there's two things you can look at: side lengths or how far they are from the center of dilation. In this one, there aren't any side lengths that are horizontal or vertical, so they would all be hard to count. But the distance from the origin or from the center of dilation I can count. This one down here, J prime, is 1.5 units from the center, whereas J was only 1. So if you take 1 and you multiply it times something, which is what we do, we multiply the original distance or length times the scale factor, and you get 1.5. Then what was your scale factor? It was 1.5. Divide that by 1 if you want to. K equals 1.5. Same thing over here. D prime is closer in, E prime is closer in, C prime is closer in. They got closer to the origin. That's a reduction. That's bringing it in. That's making it smaller. Okay, so a reduction has to be a number smaller than 1. 3/2. Don't look at it and just say, oh, a reduction has to be a fraction. 3/2 is a number bigger than 1. Fractions can be bigger than 1. That's the same as 1.5, so it's not that. That's the same as this is 3/2. That's not that. So it has to be one of these two. Okay, so what I'm going to do is I'm going to look at, and this is another way of looking at it, is my scale factor is always the new distance or length over the old distance or length. So let's look at the new one here between D and E prime. D prime and E prime. D prime is at 1, E prime is at -1/2. Wait, yeah, -1/2 in terms of the Y value. So from 1, we have 1.5 is the new distance between D prime and E prime. How far were D and E apart? 1, 2, 3. So what's 1.5 divided by 3? It's 1/2. 4.5. So that's my answer on that one. All right, number 17. It always helps to find something. Notice I went for DE and D prime, E prime because they're vertical. Always find ones that are horizontal or vertical to measure, to count your distance. What do I mean by ones? I mean distances. It can either be the distance from 0, 0, or it can be the length of the segment. So here, all the segments are sort of slanted. None of them are horizontal or vertical. But look at G and look at G prime. First of all, G prime is out here farther, so it's an enlargement. Sorry for the cat hair. Can't be smaller than 1 if it's an enlargement. Okay? So G prime, remember we just said the new length over the old. G prime is the new one. So it's 1, 2, 3, 4, 5 units away from the origin, from the center of dilation, which is the origin. And G is 1, 2 units away from it. So there it is. That's exactly what that is. It could also have been expressed as 2.5 or 2.5, because those all mean the same thing. 5/2 is 2.5. And last but not least, again, none of these sides are horizontal or vertical, so I'm going to look at distance from the center. It looks like the ones with the apostrophes are the further out ones. So that's an enlargement. Wow, guess what? That's going to give us the answer this time. All those numbers are less than 1. If it's an enlargement, K has to be, my scale factor has to be bigger than 1. So I don't even have to check it. But we could. Let's go ahead and do it the other way. If W prime is the one out here, that's 1, 2, 3 units away from the origin. or from the center of dilation. That's the new distance from the center of dilation. The old distance was 1, 2. So that's the same thing. 3/2 is the same as 1.5. Hope this has helped. Sorry it's been a little bit long, but I really wanted to make sure to go through every problem in detail for you. Thanks so much for watching.